Okay, welcome back. All right, if you remember last time we were talking about atoms that were stable, and we said that your noble gases are stable because they have 8 valence electrons. That's that octet rule. That'll become important later on as well. And we said only 6 of the atoms actually had that nice stable configuration. So what are the others going to do? Well, one thing they can do is they can pick up or lose electrons, and it's kind of a double-edged sword. By picking up or losing enough electrons to have the noble gas structure, you got a very stable atom. All right? But the problem with it is now you got a charge. And remember, the principle of neutrality says all things being equal, atoms and molecules prefer to be electrically neutral. We also talked about polyatomic ions. The polyatomic ions are kind of like molecules with a charge. The driving force behind polyatomic ions is actually very similar to the driving force behind what we call monatomic ions, single atom ions. When we start talking about structure, we'll get into that, and I'll show you how that works as well. But I've got this double-edged sword. I mean, it's good to have the 8, but I don't really want to have a charge. Is there any way I can maybe have my cake and eat it too? Is there any way I can get around the principle of neutrality, but yet still have that nice noble gas structure? Well, let's talk about ionic compounds then. All right. Recall that some ions have a stable noble gas structure but are not neutral. So here's a sodium atom. Okay, it's got that 1 extra valence electron sitting there. And here's a bromine atom. It's got 7 valence electrons. Look at the group. It's in group 17, so that's how you know it's 7. Sodium has group 1, so it has 1. So this sodium has 1 more electron than it really wants. This bromine really could use an electron. Do you see a deal to be made here? So under certain circumstances, what this sodium does is just gives the electron to the bromine. The sodium would prefer to get rid of it, so it doesn't mind it one bit. The bromine's looking to pick up 1 more, so it's happy too. Well, now my sodium has 1 less electron than what it had before, so it's got a positive charge. My bromine now has 1 more electron than what it had before, so now it's got a negative charge. What keeps them together? Well, the fact that you have opposite charges, and opposite charges attract. And folks, that is an ionic bond. And sodium bromide is called an ionic compound because it contains an ionic bond. All right? Now, why? What's the driving force here by staying together here? Well, this sodium has a nice noble gas structure. This bromine also has a nice noble gas structure. Apart, they have a charge. But when I put the whole thing together, what's the charge? It adds up to 0. And so therefore, I'm not violating the principle of neutrality, but I do have a noble gas structure for both of my ions here. I can have my cake and I can eat it too. I can't bring you a jar of sodium plus. I can't bring you a jar of bromide. But can I bring you a jar of sodium bromide? Yes, I can. I can bring you a jar of sodium bromide because it's electrically neutral. And that is the driving force behind ionic compounds forming. You've got all these ions, they have a nice electronic structure, but they're not neutral. By combining your ions in such a way that you get groups that add up to 0, then you're not violating the principle of neutrality anymore. You're having your cake and eat it too. And that's the driving force behind ionic compounds forming. If every atom had a noble gas structure already, you wouldn't see compounds forming. But this is yet another way that atoms can get around not having that noble gas structure by forming compounds, in this case ion. Okay? Well, when you write the formula for an ionic compounds must be neutral. In other words, all the ions have to add up to 0. All right? I don't think this is very difficult, but students have a problem with this. They always have problems with this, and honestly, I don't understand why. But, that's okay. You do. So it's a problem, whether I realize why or not. So I'm going to try to explain this the way I normally explain it, and I hope that you can understand it. But if you're struggling a little bit, then, I understand. Okay? So what is the formula for an ionic compound between silver and sulfur? Okay, silver forms a +1 charge. Okay, it just does. Just take my word for it. Sulfur is in group 16, so it forms a -2 charge. All those form -2 ions, right? Okay. So basically what it comes down to is what's the smallest number of little silvers and sulfurs I can put together and get something that adds up to 0. Well, I can take 2 silvers, which adds up to +2. I can take 1 sulfide that adds up to -2. What's +2 and -2? 0. So the formula for silver sulfide is Ag2S. All right? The charges are still there. You don't write them in the formula. Okay? The silver still have +2 charges, or +1 charges, and the sulfur still has a -2 charge. They're there, but you just don't write them. All right? And what keeps those 2 silvers and that sulfur together is the fact that you're opposite charges, and they're bonded together that way, and they act as a unit. Okay? What about barium and fluorine? Well, I know that barium is in group 2 of the periodic table, and I know those form what type of ions? +2. +2. All the elements in group 2 form +2. All right? I've got fluorine. Fluorine's over here in group 17. What type of ion do those form? Those elements form -1 ions. See, they can pick up 1 electron and have 10, 18, 36, 54, 86, just like your noble gases. All right? So if I have a barium that forms a +2 and a fluorine that forms -1, what's the smallest number of atoms I can put together and get something that adds up to 0? Well, 1 barium with a charge of +2, 2 fluorines with a charge of -1 apiece. That gives me a total of -2 here, +2 here. That adds up to 0. There's your formula. All right? So to write ionic compounds, formulas for ionic compounds, you got to be able to count to 0. If you can count to 0, you can do this. If you write the formula of an ionic compound and it doesn't add up to 0, you have done it wrong. Do it again. Got to add up to 0. Solids, liquids, low temperature gases have to be electrically neutral. Okay? Here's a potassium. What's this SO4? That's your sulfate polyatomic ion you're supposed to know, that you were supposed to memorize from the last video, right? Have you done that already? Get started on it. All right? Potassium forms what type of ion? Well, it's over here in group 1, so it's a +1. What's a sulfate? Well, it's an SO4. Do you remember the charge on a sulfate? -2. Sulfate's a -2. Okay? So if potassium's +1, sulfate's -2, what's the smallest number of potassiums and sulfates I can put together? Well, 2 potassiums at +1 apiece gives me a total of +2. 1 sulfate gives me a total of -2. +2 -2 is 0. So it's K2SO4. All right? That doesn't mean my 2 potassiums are together. They're both positively charged. Why would they be together? Like charges repel. It just means in the crystal structure, you've got a sulfate and you've got 2 potassiums. You might have one over here, one over here. That's not the exact structure, but generally speaking, yeah, you got 2 potassiums for every sulfate. All right, and what keeps them together is the fact that opposite charges attract. Cations and anions. All right, here's a calcium. Calcium's in group 2, so it forms +2. There's a phosphorus. Okay, it's in group 15. We said those form -3. So what's the smallest number of little +2s and -3s you can put together and get something that adds up to 0? Well, I need 3 of these calciums. If I have 3 calciums at +2 apiece, that's a total of what? +6? I need 2 of these little phosphides, what this is, at -3 apiece. That gives me a total of -6. +6, -6, 0. And that's how you write the formula for an ionic compound. The charges are still there, you just don't show them in the formula. Make sense? Okay, It seems fairly self-explanatory to me, but again, students always have problems with this. So I'm going to show you something else here. This is a trick. You know, sometimes tricks are useful. It's always better to know why something works, not just a trick. But, you know, sometimes a trick is the best you can do, right? It's called the crisscross method. What you can do is you can take the charge on this one, ignore the plus, take the charge on that one, take this number and put it down here, and take that number and put it there. So this becomes Ag2 S1, or just S. See, this is a barium 2 plus, this is a fluoride minus. Take the 2, put it down here, take the 1, put it there, BaF2. Plus 1 and minus 2, take the minus 2, take that 2 and put it down here, take that 1 and put it there, K2SO4. Take this plus 2 and a minus 3, take that 2, put it down here, take that 3, put it down here, Ca3B2. And there you go, you get the same answer. All right. Are there times when it doesn't work? Well, yes. Let's say, for example, calcium oxide. You know, calcium is plus 2, oxygen forms a minus 2 ion. All right. So if you crisscrossed it, you'd get Ca2O2. Is that the formula of calcium oxide? Well, no, it's CaO. Because if you've got a plus 2 ion and a minus 2 ion, you need one of those to put together, and you end up with the formula, CaO. Is it a fatal mistake? No, because if you get something reducible, you know, 2 to 2 reduces down to what? 1 to 1? So you still can get to CaO. So it's not something that you can't overcome. I can't say don't do it because it gives you the wrong answer. You know, that'd be a little disingenuous. You can overcome it. If you get something reducible, reduce it down. I prefer to do it the first way because that's the driving force. The driving force is to try to get these ions together in something where I get something that's electrically neutral. So you understand what it is and you understand why it is. The trick, the crisscross method, just gets you the right answer. You don't have to know what's going on to get it. But you know, hey, sometimes that's the best you can do, right? So I'd learn it the first way if I could. But hey, you always got the crisscross method there to check. This is one of the hardest things I think for a lot of students in this chapter is writing formulas for ionic compounds. I don't know why, but they just have problems. So if you're having problems, don't worry about it. You're not the only person that's ever had problems with it. If you get this right away, then congratulations. You're probably ahead of the game. All right? Okay. Last thing I want to talk about here, it's kind of a short video on this one. I think we'll go here, and I think we may just stop. And we'll talk about naming compounds when we get back in class. Let's talk a little bit about the formula unit just really quick. When you're dealing with covalent molecules, the molecule is the smallest unit. All right? When you're dealing with ionic compounds, there is no such thing as a molecule of sodium chloride, salt. All right? In ionic compounds, typically what you find is you find crystal structure. You have ions that are arranged in a highly ordered pattern. So it's kind of a lattice work, so to speak. Okay? So for example, sodium chloride, NaCl, if you were able to look at it, it's actually a simple cubic structure. And it's actually three-dimensional, but here's kind of a two-dimensional plane of it. Basically, you've got a little sodium plus, a chloride, a sodium plus, a chloride, sodium plus, chloride, so on and so forth. Okay? Notice that each sodium plus is surrounded by negatively charged chlorides. They're attracting. Notice that each chloride is surrounded by positively charged sodium pluses. And what keeps that entire crystal structure together is the fact that opposite charges attract. The strength of that is something called the lattice energy of the crystal structure. And lattice energy has applications when you're looking at things like solubility. You know, how easy is it for the water to dissolve? You know, as high lattice energy, it's going to be difficult. If it's got a low lattice energy, it's going to be very easy. And there's some other things that are going on there, but that's not really that important at this point. All right. The key here is there is no such thing as a molecule of NaCl. Okay. It's kind of like tiles on the bathroom floor. You take 2 or 3 tiles, 4 tiles, and you just kind of repeat them in a pattern over and over, and you get something that looks really, really complicated. And it might look complicated, but it's really just 3 or 4 tiles that you just kind of repeated over and over, right? Well, that's kind of what a typical ionic compound looks like. So why do we call it NaCl? Well, because writing, NaCl, 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 NaCl is kind of a pain and not that useful. So what we write is we write something called the formula unit. The formula unit is the smallest repeatable unit in a crystal structure of an ionic compound. So basically what I can do is I can take this sodium and I could take this chlorine and I could take that little pattern and I could just repeat it over and over and over again, and I can generate the entire crystal structure. Right? So this is the smallest repeatable unit of my crystal structure. It has 1 sodium, it has 1 chlorine, so therefore we write it NaCl. So for ionic compounds, technically the formula is the smallest repeatable unit, and that's the formula unit. For covalent compounds, quite often it is actually a molecule. Okay, a little bit different. We'll talk about that bonding in a little bit later down the road. All right. However, I will say this: there's going to come a time in here when we're going to start doing math again. I know you're dreading it, but it's going to happen. So, but not today. If I pretended that NaCl was a molecule and I did the math on it, it's not going to cause any error in my calculation. So mathematically, we can pretend like there's an NaCl molecule, even though technically it's not. It's actually the formula unit. Okay? So when we get there, we'll do it. But hey, I guess you need to know the truth, right? So I thought we'd throw this in here for you. Plus, I think it's in your book, so I guess we got to, don't we? But yeah, that's what NaCl technically looks like. Okay, so just think tiles on the bathroom floor. Okay, or maybe your lab, that elaborate tile pattern in lab. It's just some brown tiles and blue tiles and black tiles, and they just kind of repeated the pattern, and it just kind of covered the entire floor. Well, that's kind of a 2-dimensional example of what a 3-dimensional crystal structure actually looks like. All right, and that's what ionic compounds look like, and that's how it works. Make sense? Okay. I think that may be where we stop. I think if you made it this far, then that's pretty good. Rocking back and forth. It's kind of annoying, isn't it? I'll try to sit still. But yeah, that's probably where we're going to stop for now. And tell you what we'll do when we get back. If I gave you a name of an ionic compound, you could write the formula, right? Because, you know what the ions are, and therefore you try to get them to add up to 0. Practice. Can you play the game the other way around? What if I gave you a formula? Could you give me the name? Well, that's what we'll talk about when we get back, is we'll talk about naming ionic compounds. I will say this, I think it's actually easier than what you can do right now. It's probably easier to name a compound when you have the formula than it is to have the name and try to write the formula. So if you can do what we just did a while ago, you can definitely do what we're going to do coming up next. But that's probably going to take a little while. We're going to talk about ionic and covalent compounds. So maybe it's just best that we just save that for class. So if you made it this far, congratulations. This will probably get us down the road. And so I guess I'll see you when we get back, and we'll pick up from there. Make sure you watch everything, know what you're doing, ask questions, because, yeah, we're going to start with naming ionic compounds when we get back. And, of course, if you don't understand the stuff before, then you're going to have a hard time understanding the stuff we talk about in class. Should be Wednesday. Should be not this Wednesday, but the Wednesday after. So, yeah, I'll be around. Email me if you need me. I can certainly answer email. Good luck, and I'll see you when I get back. So, bye for now.